Welcome. In this video lecture, I am going to talk about how we can solve a dynamic lot sizing problem using IBM ILOG OPL CPLEX Studio. So in our last lecture, we discussed how we can solve this problem using Excel solver. So this dynamic lot sizing problem is also known as single level, single item, uncapacitated lot sizing problem. So for that, I'm using the same example which we have used in while we were solving this problem using Excel solver. So we have the order cost, which is $80. We have the carrying cost, or you can say the holding cost per unit per period is 1.75, as well as we have the information regarding the months. For that, we would like to develop the lot sizing, as well as we have given the demand, and we have discussed that we can solve this problem. We model this problem using the mixed integer linear programming model, and that was this model we have developed, and we have discussed this model in the last lecture while we were solving this problem using Excel solver. So we said that if the production time, or in a supply chain environment, if the purchase price is variable form, then we can use it. But if we are talking about in the production environment, if the production cost of the product is varying, then we can use this part. Otherwise there is no need to use this one. So we know that this is the order, or you can say the setup cost, this is the holding cost, this is the inventory balancing constraint, this is the initial and the last time period inventory condition, and this is the quantity whenever there is a setup, or whenever there is a order, how much quantity we can produce. So how we can model this in a OPL CPLEX Studio while considering this data set? Okay, for that I am opening the OPL CPLEX Studio. Okay, so here we have the IBM ILOG OPL CPLEX Studio. So currently I'm using the version 20.1. So for that, first of all, what we can do, we are going to create a new project. So file, new, and then we can create the OPL project. So we can given the name, project name is dynamic lot sizing problem. Make sure that while you are giving the project name, there should be no space in the name. Okay, and for in order to build the model, we need to create the model file. In order to give the data set, okay, so we need to create the data, as well as in order to solve this model, we need to create the run configuration. So these three things we needed for this project, so that's why we are finishing it. Okay, so once we finish it, now we can see that there is a run configuration. We have the model file in which we can write down the code, and we have the data file in which we can write down our data set. Okay, because I have already written down the code as well as created the data file. So let me see that if we would like to import that data file, how we can do that. Okay, so file, now we are going to import. So I am saying that existing OPL projects, because I have already developed this project. So I'm going to click on browse. Okay, so where this file is uh, available in your computer, so we are going to PC. So that is available over in production planning, and then dynamic lot sizing over here. So we can open that project. Okay, so if I click over here, okay, so this is the run configuration which I have created. So I've created the model file as well as the data file. So this is a setting file. So currently I'm not going to use this one. So I am going to use the model file as well as a data file. So in a model file, so in order to solve this problem with the help of this mixed integer linear programming model, so what we need to do is we need to define first of all the indices. And what is the index? That is basically the number of time period, which is t. So that's why first of all we are going to define the indices. So this is, so as we know that the first, the front two backslash as indicating the command, so we are giving the comment uh, this front two slashes is basically indicating the comments. So this is indices, and then we are defining that how many number of periods. So we are using the keyword int. Okay, so because we would like that the number of periods must be shown in the integer form 1 2 3 up to. So the int, and then you can name it whatever you would like. I am using number of periods. So whatever the name you like, either you can write down simple t or whatever you would like. Okay, so that is the name of the variable, and equal to, and I am using three dots. So with the help of this three dot means is that we are going to define this number of periods in the data file. Okay, so whenever you are writing equal this one, so I can also define this number of periods over here. But if you would like to define the number of periods in the data file, which is more appropriate, because once I have written down this code, so you can change the data for the multiple data, you can solve the same model. Okay, like in the data file I have written down this number of periods is equal to 6, because the problem we have is for the 6 periods. Okay, okay, so and then we are indicating the semicolon, which means the line of code is completed. And then we need to define that from where to this number of period, the range is basically, we would like to define the range, that the number of periods starting from period 1 to up to this number of periods. So this number of period is basically the 6. So that's why we are indicating the range, and then we are mentioning the periods. Okay, so that is equal to from 1 to again number of periods. So once again, this is again the name of the variable, whatever you would like, but these two are the keywords. Okay, so with the help of this one, we have defined the indices. Basically, if I am talking about, basically we have defined this one, that the T is from 1 to capital T, or you can say the number of periods, right? The next thing we need to define is basically the demand against the each month, as well as we need to define the order cost, as well as we need to define the holding cost. So for that I am using the comment command, that this is basically we are declaring the parameters and the data, and the float values we are going to define, that is the demand. So it is not compulsory that you should use the keyword float. You can also use int over here as well. Okay, because the demand is in a whole number, but I am using the float, which is also fine, keyword. And then we are saying that the demand, and now I am using the array basically. So why I'm using array, because I would like that against every period what would be the demand. So in order to define that array, so we are using capital brackets, and then in that we are mentioning the period. Okay, once we written down this demand bracket periods, so in the memory of the computer it is going to create basically 6 boxes. Why it is going to be create the 6 boxes? Because the number of periods we have the 6. Okay, and once again is equal to three dots mean we are going to define this demand in the data file. So how we can define this in a data file? We will go to the data, and then we are going to write down, remember that the demand, that is the name of the variable which we have used in order to define the demand. Okay, and then we are going to equal brackets. So it is going to be 36, 60, and so on, which is basically this values. Okay, so that is against the every month's value. So once we have defined this demand, then the next thing we are defining the order cost. So once again, so this we are defining this data in the model file. So if you would like, you can also write down this way as well. So again, three dot, and then OC would be equal to, so over here, okay, is equal to 80. So this thing is also fine, as well as you can also define this one in the model file as well. So it's up to you, whatever you would like. Okay, same is the case, we are defining the carrying cost. Okay, so once we have defined the indices as well as the parameters, now we need to tell the decision variables. So in this model, while we are solving this dynamic lot sizing problem, So we have basically the three decision variables. One is IT, that is the inventory. Another is YT, which is basically whether we are placing the order or not, or whether we are going to produce in that time period or not. Another one is basically the production quantity, okay, or the quantity which we are going to place the order. Okay, we are talking about the in a supply chain environment. So in order to define those decision variables, so the setup is basically the YT is a setup or the order. So I am giving the name to the setup, and the setup variable is what kind of variable it is. That is basically a Boolean type. Okay. So that's why we are saying dvar. Dvar is a keyword to define the decision variable. So dvar, and what kind of this decision variable is, it's a Boolean type. So setup into periods. Okay, so in brackets that is the period. Okay, that's why we are going to define, so order setup in period 1 2 up to 6. So same is the case, we are defining the production quantity. So the decision variable, I am using the quantity for all the periods, and I am mentioning that this is also a decision variable, but it's a float plus. So float plus mean it is a basically continuous variable, okay, and it's a positive variable. So due to this plus, it is always taking them as a positive values, okay. And then we are defining the inventory variable. So the only change over here in this inventory is that is, instead of writing down periods, so I am mentioning 0, 2 dots and number of periods. So why I'm doing that, I am saying that no, for the inventory variable, do not use the range from 1 to 6, but use the range from 0 to 6, okay, with the help of this dots. So this is the starting point and this is the ending point. So why we are doing it, because we are doing due to this constraint, because we have IT minus 1. So for the period 1 we need the initial inventory, okay. So we need to declare what was the inventory in the 0th period or the last period inventory. So that's why we have to mention that the range of the number of period in the inventory is starting from 0 to number of periods. Okay, so once we have defined this decision variable, next we are going to define the objective function. So here I am writing down the objective function in two way. The first way is I am only considering the setup as well as the inventory, okay, where I am saying that minimizing sum from t in periods, which mean we would like to use this sum. Okay, so for all the periods, sum it up. What it is going to be sum it up. So CC is basically the holding cost multiplied by the inventory at the end of period T plus order cost, okay, which is 80 multiplied by the setup variable, okay, whether we are going to place the order in that time period or not. So if you are going to write down this way, in order to calculate the total cost function or the objective function, so basically you are calculating the holding cost based on the idea that at the end of the period how much inventory we have, and based on that we are calculating the carrying cost. But if you would like to use this second objective function over here, how I am going to calculate the inventory carrying cost, basically I'm calculating the average inventory in that time period. So for that you are going to use the inventory we have at the end of that period plus the quantity we are producing in that period divided by 2. So with the help of this one we would be able to get the average inventory in that time period we have. So it's up to you whether you would like to use the inventory at the end of period. In that way you would like to calculate the holding inventory, or whether you would like to calculate the average inventory. Okay, so subject to, now we are defining the constraint. So this is CT inventory colon sign, that is the name of the constraint. It is always good practice to write down the name of the constraint. And then we are mentioning the inventory, that is the variable of inventory. And we are mentioning that the initial inventory, which means at the time period 0, it is equal to 0, because in a problem they didn't give us the initial inventory. So that's why we are considering that the initial inventory is equal to 0. And then we are writing down the second constraint, which is basically the inventory balancing constraint. Okay, so for that I am writing down for all t in period. So for all is a keyword, so I'm mentioning t in is also a keyword in period, so that means in these periods, so which means t is going to be 1 to 6. Okay, so I'm saying that change the value of period from 1 up to 6. Okay, 1 2 3 up to 6, and then balance this equation. So once again, this is the name of the constraint. So we are saying inventory t minus 1. So the first time the loop is going to be run, so it is write down 1. So 1 minus 1 is going to be 0. This is for period 1. So q1 must be equal to d1 plus inventory is equal to 1. Okay, similarly for period 2, for period 3, for period 4, 3, and up to period 6. Okay, so this is the constraint we have, and then we are writing down the last constraint, which is basically the production quantity constraint. So for that, I am once again writing down for all. So right, we are talking about this particular constraint where capital DT is the sum of the demand. Okay, okay, so we are saying for all t in periods, so the quantity in period t must be less than or equal to the sum of the demand. Okay, so we are using the sum function t in period. So basically what we are doing is we are summing this the demand. Okay, and then we are multiplying with the order variable, or you can say the setup variable. Okay, so till now we have completed down this one. So if I am not going to use this post processing, let me remove this one. Okay, so we can solve this problem, right? So we have, if I'm going to once we have completed the code, so we will drag and drop this model and data file in the run in the configuration, and then we can run it. Okay, so once we run it, we would be able to see the answers. Okay, so here you can see this is the objective function, this is the total cost, and these are the basically decision variables answer, which you can also see in the solution tab. Okay, so I will get back to this one, but let me write down that post processing part. Okay, if you can see in the script log right now, we are not seeing anything, but once we have written down this post processing, so post processing is basically once you get the answer, now how you would like to display this one. Right now what I am doing is, so here I am using one of the data structure which is available in OPL, that is called as tuple. And the benefit of tuple over the set over the array is that in that one you can define the multiple type of variables in one tuple. Okay, so you can, like in array we were just storing either integer or array, but in tuple you can define the multiple variable at one time. Like right now I'm using the data structure which is tuple, and this is the name of that tuple, which is the plan. So which mean in the memory it is going to be create a box, that is the name of the tuple is plan. So in that we are mentioning all three type of variable which we have defined over here, which is setup, quantity, and inventory. So basically what we are going to use, we are going to get in the plan this setup variable value, this quantity variable value, as well as inventory. Okay, so once we have defined this tuple, now we are going to access these values. So for that we are saying plan, that is the name of the tuple, and then we are saying plan for every period. Okay, so that's why we are writing plan into brackets, which is t in periods. So in order to write down the tuple, we are going to use these you can say less than as well as a greater than sign, and this is we are saying the setup variable value in all the periods, quantity variable value in all the period, as well as the inventory in all period. And then we are saying execute write ln mean write line. So this in these two codes, whatever you would like, it will going to display as it is. Okay, so we are saying current plan and show me the values of this plan. So let me run again. Now if you can see, it is going to be solve this problem once again, but now you in the script, so now you can see that. So this is basically the answer. So this is basically the setup variable value as we have defined in the tuple This is a setup. So it is saying that in a period 1 we are going to produce, how much we are going to produce, that is going to be 36. At the end of that period, how much inventory we have, that is going to be 0. So in a period 2 we are going to produce, how much we are going to produce, 60. At the end of period 2, how much inventory we have, 0. Again in period 3 we are going to produce, how much we are going to produce, 96. Okay, how much inventory we have at the end of period 3, that is going to be 11. So in period 4, so there is no need to produce anything. Okay, so that's why we are going to 0 0 0s. So in period 5 as well as 6, the same thing you will get over here as well. This is objective function answer. This is the inventory. Okay, over like in period 0, in period 1 2 3 4 5 and 6. So in period 0 y, that is the initial inventory, right? So this is period 1 in setup variable 1, setup 2, setup 3, and so on, as well as the production quantity. Same is the case in if you can go towards this engine, because we were solving this mixed integer linear programming. So you can see that there is a gap which is basically a duality gap, that is basically the linear programming as well as the mixed integer linear programming gap. So as this gap reaches to 0, which is indicating that this is basically the best optimum mixed integer linear programming solution, right? So I hope you got the idea how we can solve this dynamic single item uncapacity lot sizing problem using IBM ILOG OPL CPLEX Studio. So thank you so much. See you in the next video.